Okay, here we are in the lab again, and it is episode number 9 of Build Your Own Main Brain Microcontroller project. And so the last time we went over the MIPS core, so that was a good one. I like that one. So we still have a few things to cover for the microcontroller itself, and so there's a thing called pin multiplexing. So even though the package has up to 144 pins, there's a 64 pin package and the 100 pin package that I use on mainbrain, and there's the 124 pin package and then the 144 pin package. But even though that seems like a lot of pins, and you start hooking up 144 wires, that can be tedious, but there's never enough pins. I don't know how big a microcontroller would have to have enough pins. But so is what they do is there's all these peripherals and functions inside the microcontroller, and each one of those has to have some way to interface with the outside world. And so if everybody in there gets to talk to the outside world, then it would take more than 144 pins. So the pins have multiple functions. So you can have different peripherals share the same pin. And if you look at the data sheet and the functions of the pins, they have a whole list on each pin of what it does. So almost all of them have I/O for digital and analog, but there's all the peripheral functions, then there's the programming pins and the debugging pins, the clock pins, and you start adding all this stuff up and you start running out of pins real fast. But you can change the function of a pin at any time during runtime. You just can't use the pin for multiple functions at the same time. Once you configure it as a particular function, then it stays that function and that function only until you change it. All right, so for instance, maybe you have pin 5 is you want it to have a digital output to control some LED or something. But then you also want to be able to send a PWM signal out to control the brightness of the LED. So you could change the function of that pin at any time to switch from digital output to the PWM signal. All right, so there's not really any restriction on that. But the only restriction is you can only use one function at a time per pin. All right, so then there's also one other thing, and there's some functions and peripheral devices inside that are not connected directly to any pin. And so they use a programmable pin select feature, the PPS, and so you can program that pin or groups of pins to show up or be connected to certain pins. But it's not universal. You can't program a certain pin just to be any pin that you want. There is a certain group of pins that can be programmed for a certain peripheral, and you have to stick inside those guidelines. So that's pin multiplexing. So let's jump over to the code and take a look at how we implement that. Okay, actually I wanted to show you the data sheet first. So you notice almost all the pins have multiple functions. So that's the multiplexing. And for instance, on pin 1, it can be the analog input channel 23, or it can be an Ethernet error indicator. That's both are inputs. The AERXERR is an error indicator that comes from the PHY, the Ethernet PHY, because on this chip it doesn't contain the entire Ethernet module. It requires an external PHY module. And then we have RG15, which is IO port G15. So that's bit 15 of the IO port G. So it can be an input or an output. And speaking of IO ports, this is probably a good time to go look at the IO ports and see how we set those up real fast, because that's kind of a foundational thing for what we're doing, and IO ports are one of the most common things that you'll use in the chip. So let's go to IO ports here, and this is the block diagram. Seems kind of complicated, but it's not too bad. IO ports are very easy to use. They're probably one of the easiest modules to set up. So the official name is parallel IO ports. And so there's up to 14 registers that are directly associated with their operation as digital IO. All right, so the first thing is the data direction register, the TRIZ register. It determines whether the pin's an input or an output. And if it's a 1, the pin is an input, and if it's a 0, it is an output. And all ports are defined as inputs right after a reset. That way, when the microcontroller powers up and all the I/O lines are inputs, and that way there's no chance of contention from driving the pins into other hardware on the board. And the pins are fairly robust. You can have some pretty hard contention on the IO pins and not damage it. It'll pull a lot more current, but and that's one way you can tell if you have contention, is to measure the current of the device. If your current goes up when you do a specific thing, then maybe you have some contention and you're driving the pins into something. All right, so then you have an option of having an open drain configuration. You have a LAT register, the latch register, and that's where you read and write to the latch register. Or you can, you also have a port register, and you can read and write to the port. When you read and write to the port, that is actually reading and writing the pins. And the latch, LAT, you're reading the register that will control the pins. It's a little slightly different. It works the same, except for read, modify, write operations, and they recommend that you use read and write to the latch. You'll see me read and write to the port a lot, because most times you can do that without any problem. And so with open drain, you can have an open drain, and that's the ODC register. So the way it works with this X, whenever it says port X or lat X or TRIZ X, X is represented by A through, I think, K on some of the larger pin devices. A, B, C, D, all the way up is the name of the port, the parallel port. So you got port A, port B, port C, port D, and on up however many
you have for your specific device. So if you want to write to port D, then you just replace that X with D, and it would just be port D. Same with all these other ones too. All right, so the open drain feature allows the generation of outputs higher than VDD, so it could go to 5 volts. Many of the pins on the devices are 5 volt tolerant, even though they're running at 3.3 volts. So you can interface with 5 volt logic pretty easy with this chip, which actually comes in handy if you're like working with old school ISA bus or something like that runs on 5 volts natively. All right. And then you just use your pull-up resistors on your open drain, just like open collector. Open drain is basically the same thing. And okay, so then you have the analog select. Same thing with the X, A, B, C, D. All the ports have analog lines, although maybe every single pin in the port may not be analog select. But you have to turn this off if you want to use digital I/O, and that will get you. It's gotten me several times. You can't get your I/O port to work, and you're like, I can't figure it out. I can't figure it out. What's going on? And it almost always turns out to be this analog select is not turned off because you're trying to write to your pin or your port and nothing's coming out, and it's because it's selected as an analog input. And they're default. When you power on the chip, it's defaulted as analog. So like it said up here, we reset it, it comes up as all the I/O port pins are inputs and they're analog inputs right on top. So if you're going to use the digital I/O, then you have to turn these off. All right. So you have to write 0 to the pin that you want to use. And right here it says the default value is FFFF. So that's all 1. So if you write zeros, then you will turn off the analog function. And so it says here, if the tris bit is cleared, meaning you set it for an output, while the analog select bit is set, the digital output level is converted by an analog peripheral, such as ADC module or comparator module. So you're going to read like 3.3 volts, I guess. And it will cause it to consume more current if you do that, which you will do accidentally many times. All right, so one instruction cycle is required between a port direction change or port write operation and a read operation of the same port. All right. Then we have input change notifications. So you can set your pins, a pin or multiple pins, to trigger an interrupt when the pin changes the state of the pin. So you can go on a rising edge or falling edge, and you can even, I use this on for an I/O cycle. You can generate an interrupt on the rising edge, and you can generate an interrupt on the same pulse on the falling edge. All right. And or one of you can just do the rising edge or just the falling edge. All right. And so you can do the edge detect like that, or you can just do a value of the port. If it changes, you can trigger an interrupt as well. All right. And then there's pull-ups. There's weak pull-ups on some of the pins. And so you can use that to help your logic so that you don't have to put a physical resistor on the board. All right. And you just set that with the pull up and pull down registers. And so on the edge, detect, they have registers. CNENX enables a mismatch interrupt condition, change interrupt condition. See, here's the edge detect. You have the edge detect bit in this CNCon register. Change notice control register. All right. And we'll go over that later too. All right. And then there's the slew rate control. Some I/O pins can be configured various types of slew rate control. These are the registers here. SRCON1X and SRCON0X registers, where X is the letter of the port. And so here's your possible settings. So you can enable the slew rate control, and it's set to the slowest edge rate, and is set to the slow edge rate, medium edge rate, and the fastest edge rate. All right. And we'll get into that later too, probably. It's not, I don't use that yet anyway. Then you can do, they have special registers associated with the ports. And so you can clear. You can just use this clear to clear the port, or you can set the port, or you can invert the port. All right. And we'll go over that too later. It's pretty easy to use, but you have to use it in the right syntax. Okay, so now we're back to the peripheral pin select. So as we know, I/O ports can be either inputs or outputs. And so the peripheral pin select is configured based on that. So there's an input configuration and an output configuration. All right. And so you control those through registers. And so this is the way it works. You have this register here, and you have 4 bits, so 1 through F, and you select these pins. This is for input, so you select one of these pins as an input to this peripheral, and the bits, the 4 bits in this register determine which line. So it's like a multiplexer or a decoder. All right. And you have to have the TRIZ register set for input or output. It overrides. TRIZ register has priority over the PPS. All right. So you have to get your direction set, and then you configure your PPS. So you have to do it using this chart. You can't just look at it and figure out what's going on. They have this little chart here because not all pins can be mapped, and not all peripheral inputs and outputs can be mapped. So you have this specific list here. And so like peripheral pin interrupt 3. This is the register name for interrupt 3. So interrupt 3R for interrupt 3 register. And so this is the pin name right here. And so interrupt 3 register is set to 0 for send it out on D2. So you can set it on 1 as 1 for going out on port G8. All right. And on down the line. These last digits are the port. D2, G8, F4, D10, F1. That's the only ones that you have available. You can use all of these pins for any of these peripherals. Okay. We'll go over it one more time just because it gets confusing. It's still confusing to me, and I've been doing it a while. So, SDI for the serial. I think that's SDI. Is that I squared C? Or it might be SPI. But anyway, that's your serial data input pin. And so this is your register. And so you would write one of these values to connect this peripheral output or input to this one of these pins by writing one of these values. All right. So that's how you do the input. All right. And it's a pretty good list. See, it goes on. It continues down here, right here. So interrupt 1, this is the register you write to, and this is the value that you write into this register to connect it to this pin, this port pin. Okay. Now they has notes here. Some of them, 64-pin device doesn't have the ones with the 1 by it, and then the 2 means it's not available on 64-pin or 100-pin devices. And 3 is if you don't have a CAN module in your device, then you will not have this pin. So that this one must be for the CAN. All right. So then output mapping. So output mapping is pretty much the same as the input. Here we have the same type of deal, only in a reverse order. So you have a register here. All right. And you have 4 bits to write to it that controls this, I guess you'd call it a multiplexer. And so depending on the value in the register, then this output pin here is mapped to this peripheral output here. All right. And you can change this during runtime. All right. And that's one thing I forgot to mention in the beginning of PPS is you have to unlock the system and you have to unlock the register for the configuration bit. So that has to be done before you can change anything here, before you can configure a pin. All right, so it has a chart just the same. So here's your pin, and this is just like before. D2, G8, F4, that's the port pin. All right. And it has the same notes, except this has 4, and this is 4 means it's not available when the USB 3V3 pin is connected to BSS. We'll cover that when we do the USB. All right. And so, same idea. So this is your port pin, and this is the register associated with that port pin. And this is where, this is where you write to the register the value here. All right, so 0 means no connect. All right, you're not connected, nothing to this thing here. And so this is the peripherals that you can connect to these pins. All right. Same thing here. Just the same thing, just a little bit reverse order from the input. All right. And it has a list, a pretty good list. And see, I only use one time so far in my firmware, and I use this OC8. This is where the PWM comes out for the screen, the display brightness. So I use a PWM. We're going to go over that too later. But so this, then I connect it to, I think, RPD4, I believe. All right, and we'll look at the code here before we leave because we need to see an example. So this is a list of the registers. This is port A, and for these devices, apparently the 64-pin device doesn't have port A, maybe. But this is an example, and it has all the different ports. There's port B all the way up. So you have the analog select to turn the analog function on and off. You have the TRIZ register, the direction, input or output. Then you have the port pins themselves. You have the latch, the port latch data. Then you have the open drain register, and then the pull up register or pull down. You can have pull up, pull down. I didn't specify that clearly earlier. And these are for the change notice, and we'll go over that later. Okay, now if we look at our code, we'll come down, and so we go to system setup, and so system setup is the function to set up the system. All the system setup goes here, pretty much. And so we want to disable the interrupts, because if we run the system setup later to recover from an error or something like that, we want to have these interrupts turned off. If you just boot up from a reset, these interrupts won't be enabled just by default. But like I said, if you run this later after it's configured and you want to run this again to refresh the system configuration or recover from an error or something, then you want these interrupts off, because you don't want to be trying to configure something and have an interrupt pop off in the middle of it. So then, in order to change any of the peripheral pin select stuff, you have to unlock the system. And this is a specific unlock sequence that you have to do. All right. And this is the way you do it for the compiler, the XC32 compiler. And then for the peripheral pin select, you have to do the I/O control, the configuration control register. You have to turn the lock off. Okay. So, and then here we select multi-vector interrupt. And then the first thing I do anyway, is I just turn all the analog off. And that way it solves any time, the problem of you forgetting to turn these off later on. So if you just turn them all off, then you know they're all off. And if you want to use one as an analog, you can just turn it back on at any time. And these do not have to have the system unlocked to do that. All right. So here's an example of setting the direction of a pin. So this is port A, bit 1. So it goes 0 through 15. There's 16 bits. Usually not every single one is. So it depends on the pins of your device. But generally speaking, they're 16 bits. So 0 through 15. So this is bit 1 of port A. And it is 0, so that's going to make it an output. And that's where the signal for the buzzer goes. It controls the buzzer. All right. And then here's an interrupt. So this has to be an input. And so this is port A, bit 7. And that's a 1 for the TRIZ, the direction register. And so that's an input. All right. And then we have one here. This is an open drain input. All right. Actually, my note is wrong here. Let's take that out while we're here, huh? Because it's not open drain. Not yet, anyway. All right. So this is for port G, bit 14, and that's going to be an input. All right. That's for the halt signal. Okay. So this is the LED port, and this is the same thing. It's setting them up because we're driving the LED, so those are going to be 0. And these are all the port pins associated with the LEDs. And then we have to set for the secondary oscillator input. We set that as an input at port C bit 13. And on. That's just setting port pins. All right. And on down. Here's the change notice. We'll get into that later. That's kind of a whole subject to itself, so I want to do that separate. All right. Let's see. Oh, right here. So this is the only PPS function that I use. So I'm mapping OC5, the output compare module pin 5. That's for the PWM comes out of there, and we're mapping that to port D bit 4, which is pin 81 on the 100 pin device that I use. And so that's how you do it. This is your register for D4. All right, so and it's an output. And so this is the value that you write into here to connect this peripheral output to this pin right here. And it is hexadecimal B, which is what, 11?
Okay, so that's pretty much it for the peripheral pin select and the pin multiplexing and the I/O ports. We're almost ready to start writing some firmware, but we got to cover a couple things yet. For the compiler, we'll cover what the pragma directive means and how to do how you set a single pin on or a single port bit and stuff like that. And we'll go over that in the next video. And so for right now, I think that's pretty much it for this video. So I will see you in the next video.